Hello, everyone. Just wanted to clarify a couple things from the last discussion. The last discussion was essentially fine. Everything was correctly said regarding similar triangles, ratios, and the Pythagorean theorem. Everything was correctly said regarding these matters. Uh, One thing that I neglected to say was when we were talking about expanding similarity of triangles to all triangles by taking any triangle that is out there. Could be a right triangle, but it doesn't have to be a right triangle. It could be any triangle whatsoever. Any triangle, right triangle or otherwise, any triangle can be broken up into two right triangles. Any triangle can be a composition, a non-overlapping composition, a non-overlapping pasting of two right triangles can make any triangle that you want to make. We already know from the last discussion, from the previous film regarding similar triangles, ratios, and the Pythagorean theorem, that when all the angles of a particular right triangle are congruent to all the angles of another right triangle, corresponding angles being congruent to one another, there is similarity between the two triangles, and that involves a number of ratios that we've already discussed. So that's true. Can we expand that to any triangle? If it works for right triangles, does it work for any triangle whatsoever? Absolutely it does, because one way for sure we can see that it absolutely works that way is that we can take any triangle and we can make it or view it as a composition of two right triangles. If the two right triangles that compose the particular triangle, if the two right triangles that compose the particular triangle are each one of them similar to other right triangles. In other words, we'll say this, for example, as we had done, I left some stuff on the board, put some stuff on the board. Essentially, we said that, for example, look at this. I don't want to draw on this too much, guys. It might be more confusing than helpful at that point. But this is, this right triangle is not necessarily, this triangle, rather, this entire triangle does not have to be a right triangle. It works if it's a right triangle. In and of itself, it works, and we don't have to break it up into two right triangles, but we can break it up into two right triangles if we want. Here, any triangle you can break up into two right triangles. This is not a right triangle, and does it still work? Do all those, the similarity of triangles, the ratio of sides, of corresponding sides done in the right way, and there's so many ways it can be done, and there's validity all the way across the board. You can take ratios within a particular triangle and compare it to ratios within a particular other triangle where the two triangles are similar to one another and the ratios are equal. Ratios pertaining to what's going on in one triangle, how they relate to ratios going on in another triangle. And if the triangles are similar, you get ratios that are equal to each other. You can also compare a corresponding side to in one triangle to a corresponding side to another triangle, and you get a ratio, and then you can find yet another corresponding side in one of the triangles, appropriately done, compare it to yet another side in another triangle, and that ratio is equal to the first ratio that you got. Now, we've gone into that in some pretty good detail in an earlier film that we did on this, namely the similarity of triangles, similar triangles or similarity of triangles, ratios, and the Pythagorean theorem. Here, let's just do a little bit more of a clarification on it. If the angles are congruent, alpha, beta, 90 degrees, alpha, beta, 90 degrees, these two right triangles are similar to one another. If the angles are congruent, once again, gamma, delta, and 90 degrees, gamma, delta, and 90 degrees, these two triangles are similar to one another. True. Now, it can get rather interesting. I'll call this side length A, I'll call this side length B, I'll call this entire length right here length C, and we'll call. I mean, we can do a bunch of things here, guys. Let's make sure it's going to be done correctly here. We're going to say we can say this is length capital A, length capital B, and length capital C, the entire thing right here. Well, the real sticking point is this big A and this small a. That's not a sticking point. The big C and the small c is kind of where there's potentially a sticking point. It won't be a problem. We're going to get the right answer. But let's, for the sake of argument, see what's going on here. Big A divided by small a is a ratio, call it R. Big A divided by small a is a ratio, call it R. Big B divided by small b is also a ratio. Last time I spoke to everyone on this, in the last film pertaining to what we were talking about on this, I failed to mention something that I should not have failed to mention. My fault. I should have brought the altitude in, which is really the boundary separating the two right triangles that compose potentially any triangle, whatever triangle you want. You set it up in a certain way and you're there. I failed to talk about this, which I have highlighted in blue. That's a major flaw in the argument that I was bringing forth. So let me try to make things right. Just because capital A divided by A, look, alpha, beta 90 degrees, alpha, beta 90 degrees. This left side right triangle, this left side right triangle are similar to one another. Gamma, delta 90 degrees, gamma, delta 90 degrees. This right side right triangle and this right side right triangle are also similar to one another. The question is, this ratio, capital A divided by small a, is R. Is it true that capital B divided by small b is also R? I could say, they're similar, but what is it? I mean, capital A divided by small a is R. Fine. Capital B divided by small b is also a ratio, but it could be Q, not R, where Q and R are not equal. Well, it turns out big B over small b is equal to big A over small a, and they're both equal to R. And I failed to kind of explain the subtlety as to why it's true. Everything I told you was correct on that. Where I failed was not mentioning the altitudes and how they play into this. Well, the altitude right here, this side, which is an altitude for both of those, this is an altitude, capital H, this is an altitude, small h. Fine. This altitude belongs to this triangle, but it also belongs to that triangle. This altitude belongs to this triangle, but it also belongs to that triangle. What's going on here? What's going on here is that capital A, and again, I failed to mention this in the last film, so I wanted to kind of put this on as an addendum as a clarification of what's going on there. Capital A over small a is, because they're similar triangles, capital A over small a is equal to capital H over small h. That is true. That's definitely true. Good. Now we're going to the right-hand side. Because these are similar triangles, capital B over small b, I'll go over here. I'm not convinced they're equal yet. They are. Again, I was way too cavalier in the last discussion. I simply forgot it, to be very honest with you. Capital B over B, and this side is common to both of these. This side is common to the left-hand right triangle and also to the right-hand right triangle. This side is common to the left-hand right triangle and also common to the right-hand right triangle. Okay, so you can go either way. So you say H over, so this is H over H. Well, wait a minute, they're both, this equals that, we'll call it R, and this equals the same that this is. I mean, this right here equals that, and so, this right here, this ratio equals that ratio, we'll say it's equal to R, and this ratio equals that ratio, which is the same as that ratio. So they're equal to R again. Indeed, they're equal to each other. You've got capital A over small a, capital B over small b. Yeah, they're definitely equal to each other. Well, we can kind of say more. and here's where we're going to get, we haven't concluded this yet, but we're going to conclude this, which just keeps us in business. Big C over small c is going to be equal to that, and they're all going to be equal to r. Well, I know these two are. I just want to make sure this one's going to be equal to r. You know, that this one's going to come out equal to r. That this, if it's equal to r, that it's the end of the story. You got it all set there. If you got that, that answers everything. So we got to, once we find this, if we can find it, if we can get it to here, then that just goes up here and they're all equal to each other. Sounds good. Well, how are you going to do it? Speaking the right language vis-a-vis this phenomenon is the biggest challenge. The math itself is not really much of a challenge. We can simply say that, okay, how can I say this here? You could say this length right here, from here to here, we'll say that's small x. This length right here is small y. Sounds good. We said this is capital C is the whole thing, so never, no matter how big I make these things, there's never enough room, guys. That's capital X. That's capital Y. So I hopefully made these a lot smaller than that. We're looking at that. And all the way across, yeah, there's about no good way I'm going to be able to write this, but we already know this. So the whole thing that's great big C. So great big C is capital X plus capital Y, and small c is small x plus small y. And man, I'm hoping the ratio between the two is r. You know, you're basically trying to find here, when you're doing something like this, you're trying to find, I got other stuff written up here just to get us there. We're basically saying that capital C over small c is going to be capital X plus capital Y over small x plus small y. And man, the goal is equals r. Well, yeah, it's not too bad. I mean, we figured out what we have here, guys. I'm going to have to erase a few things here. Let me just hope we build a little bit more room here. What's going on here? Well, I'll tell you what. I mean, we just said there's a bunch of ratios going on here is what's going on. So you can basically say vis-a-vis the triangle, the big right triangle to the left, there's your capital X. The small right triangle, you know, for the big right triangle to your left, here's a length, capital X. For the small right triangle to your left, here's the length, small x. Okay. And for the chalk shows up pretty good, you guys. For the big right triangle to the right, the yellow one is the y. The blue one is the x for the big right triangle to the left. That length right there for the big right triangle to the left is going to be x. For the big right triangle to the right, that length is going to be y. And your ladies and gentlemen, it's the same argument here. You got the y here, the x here rather, and you got the y right here, and you're looking like this. Well, wait a minute. We already know that these two are similar triangles. Therefore, capital X over small x is indeed equal to capital A over small a is indeed equal to capital B over small b is indeed equal to R. Absolutely, we know that because they're similar triangles. We also know that y, let's kind of see there where we had gone on that. We had said something. Right. Capital, yeah. So we're going just with corresponding sides. We're not doing anything bad here. And then we said that. And let me just to be very accurate with this thing, guys. Now what had we said? I want to just get. Let me see what we had said here, guys. We had basically said, if you're looking at the let me go a little bit slower. If you're looking at just the left-hand triangles and the similarity that we know exists, and then later on we look at the right-hand triangles, both left-hand triangles will get looked at. They're similar to one another. We will look at that. Both left-hand triangles are similar to one another. Both right-hand triangles are similar to one another. And we'll just see how it works out with the long side, capital C, and the long side here, small c and capital C regarding the respective long sides here. We know, as we said, because of the similarity, capital A divided by small a is equal to R. Capital, yeah, right, because we had actually drawn the determination. We had done everything. See, this right here got us off the hook, you guys. Since the thing in green right here, the altitude under consideration, that's what got us out of there. That's why we were able to say this related to the left-hand triangle, and we were able to say this related to the right-hand triangle. Related to the left-hand triangle, we said this. Related to the left-hand triangle, we said this. Related to the right-hand triangle, we said that. And, well, if that was the case, we put them equal to each other. Yeah, sounds good. If that's the case, we've got, well, like I said, let me try to be a little more there's nothing wrong with what I just said here, but let me just take my time a little bit. Let me go along these lines right here with what we did with left-hand triangle, capital A, for both left-hand triangles that are similar to each other, capital A over small a is equal to capital H over small h. Sure, that's equal to R. Capital B over small b for the right-hand triangles now, for the two right-hand triangles, capital B over small b equals, once again, capital H over small h. And yeah, capital H over small h was indeed equal to R. And we know that the two right-hand triangles are similar to one another. So if this ratio is equal to R, big B over small b is going to be equal to R as well. If that's the case, capital A over small a equals capital B over small b. So you were dealing with the two left-hand triangles that were similar to each other, and we found that capital A over small a is a particular ratio. And it's equal to the ratio of capital H over H, and that's equal to R, because you were dealing with two similar triangles, one big, one small, two similar triangles, both on the left-hand side. On the right-hand side, you were dealing with two similar triangles, and that's where you got capital B over small b, and that was equal to capital H over H. It occurred again. Well, capital H over H was equal to what it was up here, which is R. So capital B over B was equal to R. That's where we got these guys to be equal to R. If that's for the ratio there, if that's the case, you can also kind of play the argument. I guess, we can do the argument a bunch of ways here. Let me just kind of try to be more or less pretty meticulous about the whole thing. Let's play a game here. Because of the similarity of triangles on the left-hand side, capital A divided by small a is equal to capital X divided by small x. So capital A divided by small a is equal to capital H. Well, yeah, it's certainly equal to capital H divided by small h. True. and it's also equal to, you don't have to write that again, but and it's also equal to capital X over small x. True. By the way, capital A over small a is equal to R. We'd already drawn that conclusion earlier. That was with the two left-hand right triangles that were similar to one another. With the two right-hand right triangles that are similar to one another, we have capital B over B is equal to capital Y over small y. Capital B over B equals capital Y over small y. Well, capital B over B, or capital B over small b, is also equal to R. Pretty interesting in that regard. What do we got here? Well, we got a very interesting conclusion. Well, there's a lot here. I mean, it's hard to know where to stop, where to start sometimes, guys, but let's go here. Can't make that y as big as I want to make it, but it's certainly, that's certainly the capital Y, and underneath is certainly the small y. So if they're both equal to R, you guys, you can multiply by small x, for this one right here, multiply by small x on each side, and capital X, you can multiply by small x on each side, and you get multiply by small x on each side, and capital X equals R small x. Capital X equals R small x. Multiply by small y on each side, capital Y equals R small y. Well, that's pretty interesting. Let's not forget, guys, we got to remember, we have that. That's pretty interesting. That means capital Y plus capital X over, small y plus small x. It depends, whatever, here I got x and y first, here I got y and x first. That really doesn't matter. Let me just kind of, just for the sake of just the aesthetics, I guess you could say, guys, we're talking about a situation of big X, big Y, the sum of big X and big Y over the sum of small x, small y is equal to small x plus small y, but this guy right here, big X is R times small x, big Y is R times small y. Well, you know where we're going on this, guys. Unfortunately, I don't want to erase anything either. But we got all these ratios here. We're hoping that thing comes out like that. Well, let's see. Let's take a look at it. We have got capital C over small c equals just the way we constructed it. Big X plus big Y is R small x plus R small y. Well, wait a minute. If that's the case, big X plus big Y is R small x plus R small y. You absolutely see where I'm going now. Let's keep going. Equals. Pull the R out of there. R times the quantity x plus y over the quantity x plus y. The quantity x plus y divided by the quantity x plus y is 1. The answer is R. At the end of the day, you guys, all this song and dance, what is it saying here? Well, big A over small a, big A over small a is R, big B over small b is R, and big C over small c is R. Yeah. You know, we can, like I said, you got it all here, guys. You can always go backwards. I'm always forgetting that we have this on film. Yeah, we spoke it as it is. I mean, at the end of the day, guys, we got capital A over small a equals capital B over small b equals capital C over small c is equal to R. And this whole thing right here is C, and this whole thing right here is big C. This whole thing down here is small c. Down here, essentially the longest side in this case, we just arbitrarily called it C. We're not using any Pythagorean theorem because we can't really do that here. There are manifestations of it or things derived from it that we could do, but that's not what we're even asking right now. We're looking just for the similarity of the triangles. And the triangle has to be something, all triangles can be composed of two right triangles. And if you get any two triangles that are out there, if you get any triangle, you can construct another triangle that is congruent to it. You can construct another triangle that is similar to it through the use of right triangles that are correspondingly similar to the right triangles that are found in the other triangle. You can break any triangle up into two right triangles. For our purposes, we can break any triangle up into two right triangles, and we can find corresponding right triangles, two corresponding right triangles to the two right triangles that we just found or spoke of. We can find two other right triangles correspondingly, each one similar to the corresponding triangles that are there. There's no, I'm sure there's a much better way to say this than I'm saying it, so let me just kind of say it like this. You could take any triangle that's out there and make it a composition of two right triangles. Then you can find two right triangles, each one having a connection with what you did earlier. In other words, you can find another right triangle that's similar to the first one up here, and we did, and you can find another right triangle that's similar to the second one right here, and that's that one, and you can put them together in the right way, and as long as both right triangles that are in a particular triangle share the same altitude, the altitudes are going to have, the ratio of the altitudes are going to be the ratio of the other sides associated with the left-hand side triangles, but they're also going to be the same as the ratios associated with the triangles in the right-hand side triangles. And that's the big thing. The capital H over small h being R applies to both sets of triangles. Those on the left-hand side, the two on the left-hand side, and the two on the right-hand side, because they share it in common. This altitude pertains to this left-hand right triangle, but it also pertains to this right-hand right triangle. This altitude pertains to this left-hand right triangle, left-hand side right triangle, but it also pertains to this right-hand side right triangle. And there's where you can, that capital H over H being a ratio equal to R, because capital H over H is equal to R, and capital H and H are correspondingly shared not only, this big H is shared by this left-hand side right triangle, but it's also shared by this right-hand side right triangle. This small h is shared by this left-handed side, on the left-hand side right triangle. The small h is here, it's shared by that, but it's also shared by this right triangle on the right-hand side. And because of that, the capital H over H being equal to R applies to both places, and you end up getting, and that was a very important point, which unfortunately the last time I spoke about it, I just didn't bring it up. I just made the assumption that it was true. Indeed, it is true, but it needed to be said. That's a main reason I wanted to do this again. So here it is for you guys. It's looking like this. So what's the moral to the story? At the end of the day, you guys, this is capital A, capital C, capital B, small a, small c, small b. They are similar. They don't have to be right triangles to be similar like that. We did our work, at least perhaps not in the most rigorous sense, but at least in a very intuitive sense. We saw that the right triangles lended themselves to easy use, to very beneficial use to us to talk about numerous things regarding ratios, regarding similar triangles. Once again, they helped us out a lot. We were able to utilize we were able to utilize the similarity of right triangles to make sure that this also works. We use the similarity of right triangles to actually get an answer like this. Now, you saw we looked at it. We looked at the Pythagorean theorem two ways in the video regarding similarity of triangles, ratios, and the Pythagorean theorem. Right now, I can't remember what the exact title was. Either a similarity of triangles or similar triangles, and then after that followed by ratios and the Pythagorean theorem. Well, you see it. There's nothing wrong with the film on that. I mean, the factual content that's there is there. It works out for us. But again, that needed to be looked at. The real big thing of capital H over small h being equal to R and applying to both sets of right triangles. Applying to this ratio applies to the right triangles on the left-hand side, and it also, that same ratio applies to the right triangles on the right-hand side. So that was a big thing to say. Now you saw that there was a really fascinating proof that had been given, I don't know by whom the first time it was given, but I had seen it a long time ago. It was a pretty simple proof, and we proved the Pythagorean theorem, and we got c squared equals a squared plus b squared. And then we looked at it another way, using ratios and similarity and things of that nature. So let's just quickly give it a view. Maybe this will go a little bit faster on that. And that'll be all I have to say, related to that. I just wanted to bring up, this thing right here. It was a pretty big thing to be looking at. Wanted to give that one a look. So, and then how it relates to that stuff. That's something I needed to see. That I thought we needed to see. So, okay, let's take a quick look at it, guys. Basically, we'll hinge it on where, area seems to be a good way to look at things. So let's do it. There's a lot here. First of all, this A right here is a hypotenuse to this small right triangle. This B right here is a hypotenuse to this bigger right triangle. And this entire C right here is the hypotenuse to this real big right triangle. The big thing here is, guys, the original right triangle had a 90-degree angle in it. This was A, this was B, this was C, but here's a real big thing. Here's theta. Here's 90, therefore this is 90 minus theta for all of these to add up to 180 degrees. We've already talked about that in the last film, so that was all right. If this is theta, and this is 90 minus theta, and that's 90, okay, sounds good. Theta, 90 minus theta, 90. Take a look here, though. Take a look at this one, the medium-sized right triangle. Here's theta again, here's 90, and here's 90 minus theta again. Same angles. How about the small right triangle? Here's 90, here's theta, here's 90 minus theta. There are three triangles here, all of which are similar to one another. And all of what pertains to similar triangles pertains here. All of what pertains to similar triangles in general pertains here, and specifically all of what pertains to similarity of right triangles also pertains here. Basically, they're similar triangles. Doesn't matter if they're right triangles or not. Similar triangles behave in a certain way, and we've gone into that in the last film, and we've gone into it some more just now. So what do you want to say about this? Well, I'll tell you what, area is area. The area of the whole thing is, here's a base, here's a height, sort of, right? If you put it on its, if you turn it upside down or sideways, you got a base of A and a height of B, and you know, area is going to equal area. So let me just walk you through that. We'll go pretty fast on this, guys. 1/2 AB. Why is that? Because that's half a rectangle. If that was a whole rectangle, or not a rectangle, in this case, it's half of a parallelogram. If I constructed another triangle as big as this big one, picked it up, and see which way I'd want to kind of put it, picked it up and then flipped it upside down so the big hypotenuse is facing down and the big hypotenuse is facing up. I mean, in other words, if I drew it like this, something like that, and then bam, like that, here's your 90 degree. It'd be the same thing. Well, the area of the parallelogram, in that case, would be the base is A, and the height is the perpendicular height, which is B. It's 1/2 A times B. Yeah, there's other ways to do it as well. There's another way to do it. How about the base C times Z times 1/2 will also give you the area of the parallelogram. So I could go C, you know, so the whole area of the parallelogram, if I took this guy without cutting it out, it'd be A times the perpendicular, it'd be AB. But since they're congruent to one another, they're of equal area. So each one, if they're of equal area, each one is half as big as the total. So the total is AB. 1/2 AB is the area of that triangle. If you found the parallelogram here, you'd go 1/2 C times Z. You'd go C, the base, times this. You go C times Z. You'd have the same parallelogram, but half of that, and then multiply by half, and you get what that is. Let's see here. You got Z, C times Z, or Z times C. It doesn't matter. Basically, guys, you're saying that's C, that's the altitude. C times Z is the area of the whole parallelogram. Cut it in half, that's the area of the triangle. 1/2 ZC, or 1/2 C times Z. A times B is the area of the entire parallelogram. You cut it in half, you get the area of the area of the triangle. So this is really where it's at. Now the way we kind of got out of it last time was we said let's cut this guy and let's cut part of this. Let's call this length X. Let's call this C minus X. If I add them together, I get C. Not a problem there. 1/2 A times B remains 1/2 A times B. Is there a way we can kind of pull this thing off? Yeah, I think there is. 1/2 ZC. Z is the altitude. I'm not going to worry about that yet. C is equal to X plus C minus X. Okay, x plus c minus x is indeed c. Not a problem. That's the case. Is it true? Yeah, and it makes sense. It totally makes sense. If I go the quantity c minus z, if I go the quantity c minus x times z times a half, I get this guy. If I go the quantity x times z times a half, I get this. And that's all this is saying anyway. Not a big deal there. There's got to be a way I can establish some kind of a connection here. The way I'm looking at it is, you can kind of look at it and see one is, okay, let's see. I could say B is the big leg, the big, of the big triangle, B is the big leg, and A is the small leg, and C is the hypotenuse. Okay, we know that. Whether you call it big or small, it's not a big deal. The big thing is, what is opposite the 90 minus theta? That's B. What is opposite the theta? That's A. So I'll tell you what, I mean, we kind of just go over here on the side and we'll figure some stuff out. We can say that the item, we can say that the side that is opposite theta over the side, the side that is opposite theta over the side that is opposite 90 minus theta is A over B. Let's keep going. The side that is opposite theta, that's x, over the side that is opposite 90 minus theta, that's z. It's actually true. Opposite theta is A, opposite 90 minus theta is B, so go opposite theta over whatever side's opposite theta over whatever side is opposite theta over whatever side is opposite 90 minus theta. Well, whatever side is opposite theta is A, whatever side is opposite 90 minus theta is B, so it's A over B. Well, wait a minute. Well, how about this theta? That's an x. How about this 90 minus theta? That's a z, so it's x over z. How about this theta here? It's a z. And how about this 90 minus theta? That's c minus x. So this is not the only way to do it, guys, but at least these ratios speak very much. Speak much. So I guess I'm looking for some way out of this thing, and I'm looking at the x, and I'm looking at the c minus x, and maybe I can do something here. To get x by itself, ignore this over here on the far right-hand side, multiply by z on each side. To get x all by itself, and forget everything on the right-hand side right here, I got it covered. Let me multiply by z on each side. Okay? True. That's x. How about c minus x? That's a little harder one to solve. But maybe I can do it. I'm not going to work with these are two, here's a problem with the x and the c minus x. If I ever knew what x was, I guess I could kind of say what c minus x is. They're pertaining to something I'm trying to solve, so it's probably good logic not to be looking to say something in terms of x or in terms of c minus x, but rather to say something else that will explain, that will be written in certain terms, and it'll explain to me what x is. It'll explain to me what c minus x is. It's probably the way I want to go. Let's not go, so I don't want to use x on this one. I can, whatever. We could probably debate a lot of things right here, guys, to be honest with you, but let's keep it, let's try to stay pretty safe on what we're doing here. A over b z over c minus x, z over the quantity c minus x, multiply by c minus x on each side, and multiply by the quantity c minus x on each side, and then multiply by b over a on each side. Again, you saw this the last time, guys. There's not much, if any, difference in the actual argument here that takes place. This is a little different ratio. We'll get to here. I think this is important, guys, because now we're kind of writing it. There's an awful lot we don't know here, but we are trying to find what c is. So the fact that we took this and wrote it like this, and the fact that we took this and we wrote it like that, that's kind of the key to the whole thing, and that gets us through it actually. Now that's what we had done last time, guys, to make this thing happen. So you're looking at those two things. Let's stay here. Bring it down a little bit. You got a half here. You got a z here. X, you know, the x we got is a over b times z. The quantity c minus x is b over a times z. And we're always referring back to that one, and we're just getting the area, we're just writing it a different way. We got it to here. Well, guys, you've got the feature to be able to reverse this. Just wanted to quickly go through it with you. Let's talk about it. You can pull a z out of here. You can factor a z out of here and put it right next to that z. 1/2 z squared equals a over b plus b over a. Let's get a common denominator. What's a times b? It's ab. A times b is ab for a common denominator. A times b is ab. Well, how are you going to get the ab here? I'm going to multiply the bottom thing by a and the top thing by a. Special one, a over a. A times a squared. So it's a over a. A over a is the special one, multiply it. A times a squared. A times b, ab. Here, you need for it to be ab, so you're going to multiply by a special one called b over b. B times b is b squared. B times a is ab. And it's equal to this. True. Again, let's remind ourselves, this is where the whole thing kind of, the beginning of the argument started right here. The beginning of the argument was right there. So what you're talking about is, you're saying basically, you've got equals, I mean, however you want to put these equally, so that's true. Well, let's put it this way. That's going to be equal to 1/2 AB. That's what we had, so we just move it up here. That was the AB. 1/2 AB is this. The hardest part of the problem is done, ladies and gentlemen. The hardest part of the problem is indeed done. You get it to here. AB is equal to this. This is 1/2 z squared, a squared, b squared over ab. Sounds good to me. What do you say you multiply by 2 on each side and then multiply by ab on each side? Get rid of this ab down here. So multiply by 2ab on each side if you want. Multiply by 2 on each side, and the half is gone. Multiply by AB on each side. Multiply by AB on each side, you got a squared, b squared. True. And let's just see where we want to go here. Now, that's indeed true. Let me try to think. Right. Well, here's, yeah, right. Okay. There's, let me kind of go. Okay, that is true, but what do we know? What do we know is true right here? 1/2 ZC is where that is. So let me just trying to think here for a second, guys. We'll talk about that in a bit. This is not This is not out of our mind yet, nor is this. Let me see where I'm going to go, guys. I didn't, looking at this, let me try to figure out where we could. Now, I did have the 1/2 in there. There's a part of me saying I shouldn't have done anything about it, but I think we're okay. Let me square root both sides. If I square root both sides, I got AB equals Z times the square root of the quantity A squared plus B squared. And I don't know that I need to put parentheses there, guys. I just square rooted both sides. True. The area, again, I took the half out of there, and I'm going to bring it in there. Just trust me on this one. Let me multiply AB by a half. Let me multiply this by a half. And that's the square root of A squared plus B squared. I'm not putting parentheses underneath the radical. I can. I don't know why I did it here. I didn't really need to. True. But guys, isn't that the same as 1/2 CZ or 1/2 ZC? That's the big one. Here's where it gets real interesting. We had gotten it to here. This wasn't bad. There's nothing wrong with this. I mean, we got to here. But getting to there is I just multiply by half again. Well, wait a minute. 1/2 ZC equals this. So at that point, guys, again, it's one of those things. You guys do have access to the reverse feature if you want to look at it. I'm not trying to flatter myself too much. You can probably go through this stuff a lot faster than I can talk about it. I'm trying to run across a little bit of space here to actually make this thing work. But like I said, when you're looking at this stuff, guys, you can probably think about it much faster than I'm going to be able to talk about it, than most anybody's going to be able to talk about it. So what do we got here, guys? We got essentially, well, you see what we got here. So we don't need to repeat too much, but let's just repeat some of it. Let's take the 1/2 ZC. Take the 1/2 ZC and set it equal to 1/2 Z, 1/2 ZC again. It's got to be ZC. You can't have two different areas. It's one area. So everything there, everything lines up, you guys. If I divide by a half on each side, the halves are gone. If I divide by Z on each side, the Z's are gone. In the end, I got C is equal to, and then we got what we said. We said, I mean, if this is true, this is true. So if this is true, so square both sides, and it remains true. Absolutely. Absolutely. And like I said, guys, the last time we had done it, man, it's a whole lot easier. It seems a whole lot easier than what I just did here. I mean, that's for sure. But there it is. That's how it looks. And so And like I said, guys, the last time we had done it was, we're here, might as well give you the quick look at it. You saw it, it should be pretty. The other one, like I said, the one we had done as the precursor to much of what we had done. It was the one we got it out of the way really quickly, you guys, when we talked about we talked about a situation where if you had this, and we said do something like that, then do something like that, then do something like that, then do something like that. And we said if this was a square, all sides equal to C, that's 90-degree angle. If this is theta and this is 90, this has got to be 90 minus theta. And again, this was got to be 90 minus theta. Here's 90-degree angle. Then here's theta again. That would be theta. Theta and 90, and what would this have to be? 90 minus theta. Here's a 90-degree angle. Here's theta. Here's 90. Here's 90 minus theta. That's 90. That's theta. Well, wait a minute. Theta, 90 minus theta, and 90 occurs in all three triangles. That's theta. That's 90. This is 90 minus theta. All three triangles have the angles. All three triangles have congruent angle. Forgive me, all four triangles. And this is a horrifically bad drawing, guys. Pretend that is a square, please. You saw it in the other film. I succeeded better in the other film drawing this thing. But you're looking at it like this. And, so we're looking at it. There's about no way this is going to look good. But so anyway, assume, well, look, I mean, each one of all four right triangles have the exact same angles. All four right triangles have whatever's in any one of these right triangles. The exact same angles are found in the other three right triangles. They're all similar at the very least. Well, they're more than just similar. If this guy's of length A and that's of length B, then that right there is of length A, that's of length B, that's of length A, that's of length B, that's A, that's B. A plus B is the length of the square's edge. A plus B is the length of the square's edge looked at somewhere else. Every side of the square is congruent with every other side of the square as far as length, has the same length. The length of each side of the square is A plus B. A plus B, A plus B, A plus B. They have, all four of these triangles are congruent to one another. So with that in mind, guys, I've somehow managed to run out of chalk. I'm not even sure how I did that, but I thought I had more up here. All right, let's just, kind of take this, get it out of the way. You saw what I did last time. The area of the entire, you're playing the same game with areas again, in a sense. The area of the entire real big square is, well, the edge is A plus B, and the other edge here is A plus B. So it's the quantity A plus B times the quantity A plus B. And then I'm going to take 1, 2, 3, 4 congruent triangles, each one with area 1/2 AB. and I'm going to take the square in the middle of all this, in a sense, the square, and it's got edge, each edge is c, so c times c, c squared. Do this by the FOIL method. Four times a half is 2. The AB stays. You got c squared. It's a great problem. Get it to there, you're almost there. Subtract 2AB on each side. Subtract 2AB on each side, and we got, well, we better get the same answer. What's going on in mathematics, the laws of mathematics cannot be changing on us depending upon how we do the problems. If we do it correctly, we're going to be getting the same answer. We're going to be getting the right answer. And that's it. And this, like I said, this particular way of proving it, wow, it's pretty fast. It's faster. It's whoever had done it, they did brilliant work doing it. It's quite simple. It's faster. It's quite simple. It's faster than what I did earlier, and this is the first thing I had shown you guys in the other film. And we used it kind of as a springboard to derive various things. Okay, thanks, guys. I just wanted to clean up. I mean, it wasn't a major deal that had to be handled, but it was certainly important that it had to be talked about. When you have a common altitude between two triangles that are synthesized without overlapping, with no overlap, you're piecing them together. You're piecing the two triangles together, the two right triangles. You're piecing the two right triangles together early in the discussion here. You're piecing the two right triangles together. There's no overlap, and they share a common altitude. And then two other triangles are pieced together without overlapping, and they also share a common altitude. And the one set of those two triangles forms any triangle you want, depending how you want to make it. Any two right triangles can be used to basically give you the composition of any triangle that you want. And then you can find a similar triangle to that triangle that you composed by using smaller triangles. Each one is similar to, one of them is similar to one of them. One of them is similar to one of the originals, and the other one's similar to the other original. And you can piece them together, and they also share a common altitude. And the common altitude allows you to talk about each pair and the great similarity that occurs between each pair composing one triangle. Each pair composes one triangle, and both those right triangles share an altitude. And that shared altitude allows comparison very, very well, and allows us to really make arguments about similarity of triangles regardless of what triangles we're talking about. It's easier done than said, as you often hear me say, but so that's the case. Anyway, thank you very much, and take care.